Hello, I'm Stefan Graeber. I'm the project leader for LXD, and today I'd like to talk about networking. LXD supports many networking options, from a simple local bridge to device pass-through, MAC VLAN, peer-to-peer connections, IP VLAN, routed network interfaces, SRIOV, or even a full-on SDN like Oven. For the vast majority of people running individual systems, a local isolated bridge, like the one you get just by running LXD in it, is perfectly fine and will do the job just perfectly. For multiple systems, things get a bit different. For multiple systems that happen to be sharing the same physical network, and where you're in charge of the network infrastructure, then quite often the easiest is to actually put your instances directly onto that physical network or on a separate VLAN on that physical network. And for that, you can use interface pass-through, a OS level bridge, MAC VLAN, OSRIOV. All of those options will work perfectly, and that will get you the best experience for that. But then you've got a situation of having multiple systems that may or may not share the same physical network. Or maybe you don't have access to reconfigure the network, or you don't control the gateway. Then you've got kind of two options for that. One is to use Oven, and the other is to use something called the Ubuntu Fan. And the Ubuntu Fan will be the focus of this video. Now, as I said, the other option would be using Oven, but Oven, while very, very flexible, also means it gets quite complicated to set up at times. It's got a lot of advanced features, but you're gonna need to run effectively a database that stores its state, that next integrates with that and configures it, and there's a bunch of dynamic tunnels, and it's great if you're running an actual production cluster, for example. It's perfectly fine to deploy for that. But if you're just messing with a few systems at home, or if you're deploying a small legacy deployment, whether it's clustered or not, in the cloud, then there are easier options, and the Ubuntu Fan is that easier option in this case. So, what's the Ubuntu Fan? Well, the Ubuntu Fan is effectively an overlay network that's built into the Ubuntu kernel. This is not a mainline Linux feature, so if you're not using the Ubuntu kernel, it's going to be missing. But for those using the Ubuntu kernel, the Ubuntu Fan is effectively a way of having like a stateless SDN in many ways. So by reusing some normally unused address space, it's possible for a machine, either 250 machines, to have up to 16,000 containers each, or up to 16,000 machines to have 250 containers each. That the way the fan works, it effectively encodes the machine's address within the instance address, so that the Linux kernel can figure out where the destination is and just send the traffic tunneled to that target machine. It's really quite clever, works really well, and we're going to be looking into this today. So what you're looking at here is the mass deployment that we use on the LXD team. I selected 3 Raspberry Pis. They're all deployed now with Ubuntu 20.04. They're all technically on the same network, so I could actually use some other networking options, but I'm not gonna in this case. And the goal here is gonna be to assemble a quick LXD cluster on those, show how LXD automatically sets up fan networking for new clusters, and then show how to attach another system that is not part of that cluster to the same fan overlay, effectively, so that its own instances can interact with the instances running on those 3 Raspberry Pi systems. So I'm just going to be switching over here to my terminal, and I'm going to open a shell on each of those Raspberry Pis. Before anyone asks, our SSH is just the wrapper I've got around SSH, which immediately sudos over to root so that I don't need to do it myself. Alright, so I've got a shell on all 3 of those Raspberry Pis. I also have a shell on my local machine, which has an empty project that I can mess with. Now, LXD comes pre-installed with Ubuntu 20.04. I'm just going to be refreshing that over to the latest release of LXD, so they all run 4.19 that way. Just going to copy paste that to all 3 of them and give them a few seconds to download and update. Once that's done, which should be very soon. Okay, starting. Okay, just gonna run LXD init on the first one. Let me zoom onto that one. There we go. So I'm gonna be using clustering. Using its IP is fine. I'm gonna be creating a new cluster. It's called rpi01. No need to set up password authentication for the cluster. It's gonna be using join tokens instead. Sure, a local pool using ZFS is perfectly fine. Not using a dedicated partition, 30 gigs is plenty for this use case. No remote storage, no integration with NAS. There it's asking whether I want to use an existing bridge host device for the networking. So I'm going to keep the default of no, at which point we can see that the next question is whether we want to use to create a new fan overlay bridge. So LXDNet detected that we are on Ubuntu and the kernel supports it and therefore offers it as an option. Saying yes, it then asks about what the underlay is. So that's what subnet is shared with all of your machines. If I leave it to auto, what it's going to be using in this case would be this, I believe. And while it would work for all 3 Raspberry Pis because they all happen to be on the same subnet, my laptop is not on that particular subnet. So I just need to widen the subnet a tiny bit to using this instead. By doing that, I effectively now limit the number of instances I can run per system. With the /24, as it would have done automatically, each one of the Raspberry Pis would have been able to run 16,000 containers, whereas by using a /16 for the network side of things, then they are gonna each be limited to 254. That's not really an issue. We're not going to be running more than that anyway, but just something to keep in mind. And the rest, just using the defaults, cluster is initialized. And now I just need to cluster add rpi02 and rpi03. That's their joint tokens. And I'm going to be running LXD init on both of those. Give them a few seconds. There we go. Clustering, yes. IP address is fine. Join existing cluster. And join token here. And just using the defaults for everything. There we go. This one, same deal. Joining existing cluster, yes. Do you have a join token? Yes. Dump the token in, yes. And the defaults. At which point I can just go back to showing just the first one and release the cluster now. You can see we've got 3 Raspberry Pis all in there. And let's just launch some Ubuntu instances. So simple Ubuntu 20.04 container deployed on, most likely it's going to land on the first cluster member, so it's going to land on rpi01. Once that's done, I'll do the same 2 more times so that we get a container on each one of the Raspberry Pis. So the first one is good. Second one must be transferring the image within the cluster. There we go, it's done. Now it's unpacking the image on the second Raspberry Pi. And just as a reminder there, the initial creation is quite a bit slower because the first Raspberry Pi had to actually download the image from the internet and then unpack it locally. The other two don't have to download from the internet, they just download from each other, but they still need to unpack the image for the first instance that's created. It gets significantly faster after that. So now the third one is getting created. And just for kicks, we can create another thread to show that things are significantly faster once it's no longer the first instance on a particular system. So that's it for a second instance on the first one. You can see that the bulk of the time being spent is just remapping the file system before starting. Okay. And one to go. There we go. So that's 6 instances running on that cluster made of 3 Raspberry Pis. And if we look, you can see they all got IP addresses that kind of look similar. The fan network defaulted using 240.0.0.0/8 as the default subnet. And now if you look at the middle of the address, you'll see how the fan works. So U1 here is running on RPi01. RPi01 has IP address 172.17.16.8. Now, the mask we entered earlier meant that 172.17 is the local network, and then the rest of the address is the host identifier. Which means that if we look here, we see 240.16.8.108. The 16.8 in the middle is the same 16.8 we have here. And that's how the fan knows where to route the traffic. And we can see this one is running on the second one, so it's got 16.7. This one is running on the third one, it's got 16.19. And that lines up with that 16.7 here and 16.19 here. So now if we go in the first one and ping the second one, this just works. It effectively sends the traffic onto its host, so in this case RPi01. RPi01 extracts the target address from the IP address being reached, and then sends the traffic encapsulated to that particular system, which then forwards it onto the destination container. So that works really well. In this case, it's all within one cluster, so all the instances can talk to each other, it's fine. The issue is if you're coming from an external system, say my desktop here, and I ping this, it has no idea how to go to it because this is effectively an overlay network and you're not part of the overlay. So there's no super good answer to that. You can manually configure that system to join the fan. That's one way to do it, and then you can access those instances. Or most likely what most people do is that they will add a proxy device to the instance to actually forward traffic going onto the host, in this case RPi01, onto a given port of the instance. But in this case, what I'd like to show is how you can add a completely standalone LXD, so in this case my desktop machine, to the exact same fan network, and then the instances running both on my desktop and on that RPi cluster will be able to talk to each other. So for that, you need to create a new network. Let's call it fan BR0. It's the type is a bridge, but that's the default. It's what we need is bridge mode equals fan, and then fan dot underlay network, I believe is the name. Then set that to the same value. Actually, I can just check what's used here on the Raspberry Pi cluster. So yeah, fan underlay subnet is the key. So fan underlay subnet and 172.17.0.0/16. Okay, so now I've got a bridge here. So if I launch, let's just do initially just launch a quick VM. So that one is going to be on the default network, so it's not going to be able to talk to the fan. Well, it needs a tiny bit of time to boot up, but let's already start the second one. So the second one I'll call it V2, and that one I'm going to ask LXD to place it onto fan BR0 instead. Let's zoom in that terminal. Okay, so the first VM has started, and we can see it's got a 172.17.250 completely unrelated address. That's actually going to be reachable from the Raspberry Pi cluster because that's routed on my local network. There's effectively an address directly from my home network. But this would not be able to reach into the Raspberry Pis because it's not on that 240 subnet and has no way to get there. However, if you look at v2, we can see that that one is on a 240 address. And in this case, it's on 240.250.1.1.15, which, based on what I said earlier, means that my host system is reachable at 172.17.251. Now, if I try to reach one of the Raspberry Pis, well, one of the instances on the Raspberry Pis, this works just fine. And similarly, if I go in one of the Raspberry Pi instances up here and I get the IP address of that VM on my laptop, or on my desktop, it also works just fine. So this really shows how to just clean out things a bit, how to easily have multiple, even independent LXD deployments, still be able to route to each other and have instances just effectively on the same network. One reason why this is particularly useful is if you're on Wi-Fi, you can't, like the way Wi-Fi authentication works means you can't bridge it, you can't do MAC-VLAN, you can't do any of those things. The only way you're gonna get two systems on Wi-Fi to actually have instances that can talk to each other, well, actually, yeah, I can think of more than two actually, but is either running a full-fledged SDN like Oven, or using something like the fan, and that will work just fine. The other options end up being quite complicated, which involve like having dedicated subnet per system and your router participating in that and routing it. It's doable, but it's really hard. Similarly, this kind of solution works great in the cloud, where the cloud provided network sometimes might look like it's a shared layer 2 network, but often is really filtered and kind of fake layer 2 in many ways. This will let you have LXD running on a number of cloud instances that can all run LXD containers that can then talk to each other just fine. There are a few limitations of using the Ubuntu Fan. Like, it is very simple, it works really well, but it's not as flexible as a full-fledged SDN. The way it works effectively is if you're talking from one instance to another, that goes directly from one to the other. There's no NAT or anything involved there. If you're going to the outside world, you get NATed by the host of the instance. There's no centralized routing or router or any of that kind of stuff. So whatever system you're on is the machine you're going to be going through, going to the outside world. Similarly, there's no magic around things like DNS. Within a LXD cluster, we've put some logic in place so that DNS will usually work fine between those instances, despite not being really on the same network. But across multiple systems, like in this case on v2, if I ping u6.lxd, it has no way to resolve that. That's just not going to happen. Whereas in this case, within the cluster, it does work. As I said, LXD has logic that makes that function. But coming from the outside of the cluster, so another standalone LXD, this is not going to work. Another quite obvious limitation due to its design is because it encodes its host address in its own IP address. If you move an instance between machines, it will change address. I can probably demo that quite easily actually. So if we shut down U6, which was currently on RPi03, and I move U6 to RPi02. So it might take a few seconds because I need the ZFS to actually do a migration. Okay, so now, oops, it's already stopped. U6 is on RPi02, and if we start it back up, So as a reminder, it used to have 240, 16, 19, 117, and now it's got 240, 16, 7, 117. So it is keeping the same instance address, effectively the 117 at the end, but it has changed host, so the middle 2 digits change. So that's quite an obvious limitation of the fan, but if you need clusters and be able to reshuffle things kind of at will, that might become a problem. Like you can avoid some of that by running DNS and relying only on DNS and never on the addresses. But if you need stable IP addresses, then you might want to look more into something like Oven instead of using the fan. Anyway, that's it for a quick look into the Ubuntu Fan and how it works within LXD clusters and how it works also between independent LXD deployments. As I did in this case with my standalone desktop, reaching out to this cluster. It is really neat. It works really well. It's definitely a great way to get cross-instance networking set up very easily, both in the cloud or at home. And for something more complex, we're gonna have YouTube videos in the near future going over how to set up Oven, which is the much more featureful advanced SDN that LXD supports for more complex and more flexible use cases. I hope you enjoyed this. If you've got any questions, you can leave them below in the comment section, or you can go on our community forum and ask us there. And see you in the next one. Bye.